Good afternoon for everyone. First, I would like to thank everyone to be here. That is, thanks for that. Okay, today we have the pleasure to have here with us here Professor Roland Fischer. He is a collaborator. Just to tell a few words about him. Okay. First, I would like to tell how this collaboration starts. After that, I'll tell more things about him. First, this collaboration started in about 2017. One of his PhD students wrote an email for Augusto da Silva. Augusto da Silva was a previous PhD student from Douglas Franco from our institute, and after that became a postdoc in my group, studying clusters. And then the student wished to get some structures that at that time we have to build up some images. And then we told for her, Augusto asked for me, so send the structure, everything, and tell for her that we also can perform some calculations too, in case that's necessary. From that on, this initial discussion ends up with a Gavin-Chemie paper that was published in 2018, was a cover letter in the Gavin-Chemie. After that, several opportunities was built up in, then we come up new papers that was published together. We received two of his PhD students in 2000, I think it was before the pandemics that they come here. Two of them, we have a small workshop here together. And then this year, then we start to make a paper that we have the goal to go higher, as always, Roland wish. And then we come up to a publication in Nature Chemistry this year. This takes a lot of work, a lot of, to say, how to answer the proper referees and how to improve the paper beyond of that once you read the reports. And then to that, I have to thank Marcus Kills a lot because he was the one that joined the paper after we submitted it because we need to rewrite everything that we have done from scratch. Okay, and this requires a lot of work, but at the end, it pays off. We was in the Nature Chemistry, and then this collaboration is very fruitful for both teams because we combine together our expertise that we have because we have done a lot of cluster studies in the past, but then we need a room where to go beyond of that. And what we decide to go to metal complexes by the motivation from the collaboration with Roland, okay? Of course, my connection that I have previous with Germany helps a lot to the discussions and then so on, because it is really a pleasure to have the higher level discussions with Roland. Okay, Roland has a long history in the chemistry. Today is one of the most cited researchers with 8 indices, above 100, with many publications, many citations, leading a group that is a reference and became also director from the Catalyst Institute there in the Technical University of Munich, in Garching, a place that I have been the pleasure to visit 2 times. And then as a well-recognized scientist, and as he told us at lunchtime, okay, this project, we can take risks, don't worry. I'm already close to retire, and now I want to take the most risk ever, okay? And then, it's the first time that he is in Brazil here. Okay, Roland, it's really a pleasure to have you here with us. Okay, just thanks, Roland, for wanting to be here. That is really a big effort. Roland, thanks a lot.
Thank you very much, Juris. Thank you very much. This was a very warm welcome. So, okay, ladies and gentlemen, it's true. It's my first time in Brazil. It's my first time in San Carlos at this place. But as you have heard, there is a long relationship we have. Okay, I imagine that most of you may not have the background in organometallic synthetic chemistry, which I will now confront you. So this will be tough. But I try to make it short and entertaining. So first I explain the title. Living Libraries of Intermetallic Superatoms. So there are a lot of interesting words in it. So superatom is an interesting technical term. Some of you may know about it. And a library is always clear. We have libraries in our building as well. But what is a living library? So if you go to biosciences, drug discovery, etc., there is a huge knowledge about the chemistry of evolution and reproduction and so on. So living is a technical term occupied, of course, by living objects, and in chemistry would be autocatalytic and self-replicating and so on. That is not what is possible with my intermetallic superatoms. So the library is something where you have a series of compounds. And usually, if you go to the library in your building, it's static, except people buy new books. But the book itself would be on the shelf, and it would be a static thing. A living library is shelves with books, and there is a continuous shuffling around of the books. One is coming, one is going, some pages are missing, and so on. So a living library means you have a scenario of objects on your shelf, which is not static, which is metastable, and some of these objects talk to each other and may change. And this is why we borrowed the term living for our libraries. Okay. Now the background of this science is the periodic table. I am an inorganic synthetic chemist, and as you go back to some of your freshman classes and so on, you may recognize that the inorganic chemists, maybe also the theoretical chemists, but the inorganic chemists, they are proudly presenting themselves. We are the heroes of the periodic table, all elements. So 80% of the elements of the periodic tables are metals. And this was attractive to me when I was a student. So I wanted to play with all these elements, etc., etc. Catalysis needs metals. Okay, there is organocatalysis as well, which is now a Nobel Prize and so on and so on. Maybe we have a metal-free catalysis scenario in the future. But currently, industry relies on noble metals mostly, not only, but many processes are noble metal, precious metal dependent. However, the periodic table will give you lots of opportunities to have catalytically active metals if you do it right. And sometimes you can even substitute precious and rare metals if you mix abundant metals together to emulate the catalytic property of the precious one. So this is a far background of the whole thing. So now boiling it down to the simplistic inorganic synthetic chemist, oh, fantastic. That's a playground. And my playground is the blue ones and the red ones. So I like to combine the aluminum and the gallium. Okay, I admit gallium is not an abundant metal, but it's close to aluminum, which is abundant. And if aluminum is too difficult for us, then we train with gallium. And we have the zinc, and we have these abundant metals, iron, cobalt, nickel, and so on. And alloys of them, intermetallic phases of them, they may be interesting for catalysis. So this is the far goal. We are not yet there. Many other people try it. We also. Okay, so a challenge for the organometallic synthetic chemist is the following. What means organometallic? So we play with the metal atoms, and you wrap the metal atoms in an organic ligand shell. This is like my coat. I am the metal. This is the hydrocarbon-organic shell. And if I, the metal, would lose my coat, I would not stay as a small cluster. I would aggregate, I would grow, I would become a chunk of metal. So to prevent the aggregation of metal atoms, in solution, we need ligands. And we use ligands which are organic. And ideally, these ligands are not very tightly bound to the metals. If they are too tightly bound to the metals, bad, because we can't get rid of them. My library of compounds would be a rigid one, not living. So I have to use labile hydrocarbon stabilization. And another thing is important. Look closely to the cartoon. You see this is a bowl. Well, it's a very abstract thing, but it's open here. If I would disguise myself completely with my coat, a substrate, a reactant, a partner could not approach me, right? Because I am coated. So to be reactive, there must be access to something. Now we have three cases of our targets. We want to mix metals, two of them, and we want to coat them, and we would like to have access. Now, case one, metal number A is inside, metal number B is outside. The case B, inverted. Metal B is inside, and metal A is outside. And case C, everything is randomly mixed. These are the three possible abstract cases which we are after. Okay. Now I walk you through this synthetic diagram. So what is shown here? Here is shown the organometallic chemistry we are doing. Now this is basically because, however, all our chemistry would die if we do it under the ambient conditions. We must go under nitrogen or argon atmosphere into a glove box and avoid any trace of water. If there is oxygen or water, we get oxides, no molecules, no clusters, everything is dead. So it's a very sophisticated organometallic synthesis chemistry going on. Then we have two components of the metal 1 and the metal 2, and the R means this is just the organic codes what I introduce when I start with these components. These are components we can synthesize. Some of these components we can buy by chemical companies, but what the chemical company can give us as a precursor compound for this chemistry might be too stable. If the shelf life of such a component at the industrial supplier would be short, they cannot make money of it. So our precursors typically are highly reactive organometallic compounds. We have to synthesize it. So my students cannot buy the precursors, they have to cook them. So my students need to do all the textbook chemistry they learn in organometallic classes. Now when we combine these two different precursors, we activate a series of fundamental reactions. It's like in organic chemistry. You have certain typical reactions known in textbook literature when you study organic chemistry. Same in organometallic chemistry. We have oxidative addition, we have reductive elimination, we have transmetallation, we have lots of things going on. We call it a cooperative chemistry between the precursors. So the individual precursor is not alone, it will talk to the partner. And this cooperative talking of the two is the key to drive the system to make mixed metal compounds. Two things can happen. We can get intermetallic clusters, or we can get intermetallic nanoparticles. What's the difference of the cluster and the nanoparticle? Now the cluster is a finite atom object, maybe 10 atoms, 20 atoms, 50 atoms of two different metals together. A nanoparticle is something of 500 atoms, 1,000 atoms, 10,000 atoms. So the same chemistry, the same precursors may give us discrete clusters or nanoparticles, depending on the conditions. It's interesting to get the nanoparticles as well, and we have done it. And we can do catalysis with the nanoparticles in colloidal solution, making them by the same chemistry. But downscaling matter from the bulk over the nanoscale down to the atomistic level where every atom counts, that's the goal. So basically what we want to do, we want to stop the cooperative kind of alloying process at low molecular weight intermediates. Now look at this triangle here. This triangle is the following. In the brown corner here, you have a copper. This is also a copper, and the blue is aluminum. So this is a 3-atom cluster, a minimal model of copper-aluminum alloys, the smallest entity you can make, bring together 2 coppers and 1 aluminum. And what is not shown is the hydrocarbon coating. I just left it away. It is not important at the moment. But you have to remind yourself, this is wrapped into this hydrocarbon shell. But this is not the only thing what is on this display. We have this copper 7,8, aluminum 6, and we have the copper 4, aluminum 4, etc., etc. Message is, by combining certain specific organometallic precursor compounds, by knowing about their cooperative chemistry, you can create clusters with a distribution of sizes. And this is shown here. So this is part of the copper aluminum cluster landscape, which we can obtain by just combining the copper precursor and the aluminum precursor. On the x-axis here, we have the number of core atoms. So we count together the copper and the aluminum. So 10, 20, 30, etc., 50 atoms. And here is the proportion of the copper. So for example, our small candidate here, 2 coppers, 1 aluminum. The candidate over there would be a copper 8, aluminum 6, and all these circles here and the squares mean. These are candidates, these are clusters, these are compounds we can make and isolate, characterize rigorously by X-ray single crystal structure analysis, NMR spectroscopy, IR spectroscopy, by all kinds of spectroscopies precisely. However, there's an awful lot out there. Selectivity is per definition low in our synthesis. And it's also intentionally low because we do not know which of these aggregates and clusters is an interesting one. We don't know this one might have an interesting chemistry, catalysis or something. So rather than hunting for a specific one, we want to open the diversity of the chemical space as wide as possible. So we get pitch black solutions with a dispersion of many species where you cannot isolate easily each of them. If you try it, the distribution may change. So if we hunt for one of these, we change the others. The yield for some of these may be low. For example, the triangle is fairly good to make. It's about 30% yield. But something like this here, it's an M55 cluster, the one you have mentioned in the Angewandten paper. This is crystal picking. So out of the pitch black solution, after 3 days of waiting, you collect, let's say, 5% of yield as single crystals from the glass wall. Okay. Now, what is the method to shine light into this library of things? This is high resolution mass spectroscopy. So I show you here on the copper aluminum example several mass spectra or cutouts of the mass spectra. We take it from the solution in the glove box, we inject it in our mass spectrometer, and we analyze the patterns we see, and I will comment on this in a little later. And what you also see is the 25 minutes, 35 minutes, 50 minutes, 18 hours, 3 days. And what you see without too much worriness, you see changes. This is why I say these libraries are living, because they have not reached a stable stage. Well, if you wait a week or maybe a month, it may level off, and then you are reaching a metastable situation after many, many days. However, if you look very closely, and I read this kind of formulas to you, then let's say that we have these 4 peaks here. These are all molecular ions of clusters we could isolate from this particular solution. This is the copper 8 aluminum 6. This is the copper 7 aluminum 7. This is the copper 6 aluminum 7. This is a copper 7 aluminum 6. And it's a hydrogen atom, copper 7 aluminum 6. So all of these are super close in composition. And it's plus minus 1 metal atom. They are basically all balls. You will see in a minute, they are all spheric somehow. And they are coated with more or less the same kind of hydrocarbon coat. There is absolutely no way to separate these from each other. So they co-crystallize on the crystallographic positions in the elementary cell of the single crystal you create. So even in the best case, when we narrow down the selectivity, we call it size focusing of our synthesis, we may have a dominant cluster, maybe that's 90%. So on the crystallographic position of this cluster, 90% is occupied by the, let's say, copper 8 aluminum 6, but the other 10% might be occupied by the hydrogen copper 7 aluminum 6, and you cannot get rid of that. It's an intrinsic problem of the dispersion which we are intentionally create. And if you go from this here to there, you see a simplification of the mass spectrum. So by tweaking the conditions, by playing with the time, with the concentration range of our precursors, we can influence the nucleation and growth of the clusters in some way. At the moment, this is done by stomach feeling of the informed chemist. There is no logic. There is no theoretical guidance in this. But we can narrow down the diversity space. And if we do that, we are able to come up with single crystals of typically co-crystallizing candidates. So these images here, these plots, are experimental X-ray diffraction data, which we create by fitting the X-ray data to a model where we put the clusters with occupation factors on the elementary cell positions. And then, of course, we go to our theoretical partners, and they do the quantum chemical modeling and the electronic structure characterization. Let's discuss the electronic structure first. What you see here is are the cluster valence electron orbitals of these two clusters, and they have a very nice symmetry. It's almost a spherical packing of the copper and the aluminum, and what you get is a 1s symmetry kind of low-lying cluster valence electron orbital. You have p-type, you have d-type, and you have again s-type. Now you see here the one principal quantum number, and if a student in the first year of chemistry would say in the hydrogen atom there is 1s, 1p, 1d, you would get 0 points for this answer. Now this is different in a situation when your electrons are not in a electrostatic field from a point charge, like in the hydrogen atom. If the charge is distributed over a finite volume, which is what we have here, then the angular momentum has a different restrictions, and the solution of the Schrödinger equation allows the combination of angular momentum with the principal quantum number 1 in this fashion. So this is a superatom model. Why superatom? Because the shape and the symmetry of the molecular orbitals of these clusters emulate, so to say, what we know from the hydrogen atom. And the energy sequence is different. So we would have in the hydrogen atom, we would have sp and then again sp and then d. But we have here, because of the different situation of the distribution of the nuclear charge of the finite volume, a different level of sequence of energies. But the symmetry is the same. So that is basically what the superatom model is about. Now, if you look to these two cases, this was a crystal which contains the copper 8, aluminum 6. And if we count that, we come up to 20 electrons. This is filling all this up to the 2s level, and then you have a homo-lumo gap to the next level. Now, if we have the copper 7, aluminum 6, which we can make without the hydrogen, it would be a 19 electron system. Now recall, what happens in the periodic table if you go to a situation 1 electron short for shell closing? You will have a very highly reactive radical. And this is exactly what we have here. So this is why a copper 7, aluminum 6 would capture a hydrogen radical from wherever it can get it, from the solvent or from the hydrogen. And we can do that. We can deuterate the solvent. And if we do that, then we have a D on this position. Now, this is even a more purified situation. We have done the synthesis of our rich copper aluminum library in a way to have just these two in our mass spectrum and in the single crystal. And we did it in a way to avoid that the copper gets a hydride. So here we have the copper 7 aluminum 6 and the copper 8 aluminum 6 as the only two candidates in the experiment. So the prediction is the copper 8, aluminum 6 is closed shell and a more or less silent component. But the copper 7, aluminum 6 is 19 valence electrons, so open shell, it must do something, and it does. So if we treat this kind of mixture with, for example, a hydrocarbon, in this case it's a silane, or with additional copper. So we make these compounds here, we crystallize it, we have single crystals, we know exactly the composition. 2 experiments. One is treating the solution with this silane, which is a hydrogen donator, or treating the solution with our copper precursor, which is just donating copper atoms. Now, since the copper 7 needs 1 electron to be happy, it just takes 1 copper atom, not 2, not 3, just 1. And this is exactly what happens. And since 1 electron, the cluster doesn't care whether the electron comes from the copper or from the hydrogen atom. So the thing is happy with taking the hydrogen atom as well. So this nicely proves 2 things. It proves that the superatom closing, shell closing model is working in these systems, and it also shows that we have more reactive and less reactive clusters, and it also shows some clusters may be easier to grow or to add metal atoms, others won't. Now this is the thing what you mentioned. This is the big copper 43 aluminum 12 cluster where we have all the coppers inside and the aluminums outside. And this is a so-called free shell Mackay icosahedral cluster, and there is also famous reference compounds because the metal atom count 55 is a magic number in terms of icosahedral shell packing. I skipped that. This is a detail for the kind of crystal scientists and solid state chemists. What is more interesting is the electronic structure of this whole system. Just look at this energy levels, and it's a little bit sophisticated to do the calculation. This has been done on a copper 43 aluminum 12 plus entity, leaving away all the hydrocarbon ligands and coming up with this kind of level splitting. So what happens here is that in the LUMO section of this cation, so to say, we have a situation where 3 orbitals here and 1 is coming very, very close. This is the 1H and the 3S superatom orbitals. And in the neutral compound, where we have the hydrocarbon ligands put on, these levels accommodate 3 electrons. So it's a 67 open shell superatom in this case, and they have a paramagnetic ground state with 3 unpaired electrons. We can measure that with magnetic susceptibility measurements. In this case, because of the closed dense packing with the organic ligands, there is no access to the surface. So this particular cluster, different from the other one, unless it's a paramagnetic one with being short for the shell closing, which is 68 in this case, it will not add a copper atom and it will not add a hydrogen because there's no access to the surface. This is when you remind my cartoon from the beginning, if everything is completely sterically shielded, there is no chemistry. Second example, which relates now very closely to our breakthrough result is in what was mentioned. Now, I left out the whole complexity in this diagram. I just put some of the isolated zinc copper clusters which we can make. We have number of copper atoms, we have number of zinc atoms. Again, you see this kind of triangle here. Now it's not copper 2 aluminum, it's copper zinc 2. And I will tell you on this example, there is a rationale. Why can't we make copper 2 zinc? Why is it copper 2 aluminum and not aluminum 2 copper? There is a reason for that. Simple electron counting. Each of the zinc atoms here provide 1 electron for the cluster valence electrons. Why? The zinc is binding to this hydrocarbon ligand. The hydrocarbon ligand takes 1 electron away from the neutral zinc. Zinc has 2 valence electrons. 1 is taken away by the ligand. 1 valence electron is left. So each of the zinc brings in 1 electron. So we have 1 electron here, we have 1 electron here. Now the question is, how many electrons from the copper? Now the ligand takes away 1 electron from the copper. Copper in the gas phase, ground state is D10S1. So this S1 is taken away. So this is a closed shell D10 copper atom, 0 electron available for the cluster binding. So this is a 2 electron metalloaromatic free atom cluster. This is why there is no way to make a copper 2 zinc 1, because you have only 1 electron to hold the whole thing together. In our aluminum case, where you have 2 coppers and 1 aluminum, the copper brings in nothing, but the aluminum brings in 2 electrons. So you have again a 2 electron triangle, which is metalloaromatic. So there is a logic if you do the electron counting right. Now, I can stress the discussion a little bit what the ligands are doing. Now look on this case of copper 4, zinc 4. It's a nice tetrahedra embedded in a tetrahedra. So let's look first on the left one. So the red atoms would be copper here and the green atoms would be zinc. You can recognize a tetrahedral here, but all the green ones is also a tetrahedron. So each of the zinc would bridge threefold a face of the tetrahedron. Now in this particular case, we calculated that and we crystallized it. The CP stars are the organic ligand here is bonding to the zinc, and this kind of an isonitrile ligand is bonding to the copper. And this is the outcome of the X-ray crystallographic analysis matching with the NMR and the IR, where you can assign the binding of the ligands to the different metals. Now, if we invert the situation, when you say, okay, let's put the zinc inside and the copper outside, let's put the CP stars to the zinc and, let's put the CP stars to the copper and the isonitrile to the zinc. This is also a structure which you can calculate. It's theoretically completely okay, but it's 2.1 electron volt above the minimum. And from the stomach feeling of the organometallic chemist, this makes an awful lot of sense, because in metaphoric language, the isonitrile ligand is a soft binding ligand, and the copper is a soft center, so from the hard and soft acid and base principle. Now the soft ligand goes to the soft center, the CP star is a harder ligand, it goes to the harder center, and this is nicely shown here. Okay, so if we have 8 atoms, 4 coppers, 4 zincs, we have this tetrahedra in the tetrahedra, and we have the copper inside and the zinc outside. Okay. Now we go to the literature. People similar to your group are doing a lot of calculations and a lot of physical chemistry on naked clusters, metal clusters, no ligands. Either they make it in the gas phase and do spectroscopy, ultra-high vacuum, molecular beam technology, etc., or they do it puristically in the computer. Now these people, they have done a puristic computer analysis of the shapes you can get if you put copper and zinc systematically together. Now let's look at this situation here, which is 4 coppers and 4 zincs. This is this one. This has a total different shape. This is an octahedron, 1, 2, 3, 4 coppers. 2 coppers are in the octahedron and 2 zincs are outside. While our system is much more of higher symmetry. And this again has a logic in terms of the electron management in the whole system. Now, here you have a total of 12 electrons, 8 coming from the zincs and 4 coming from the copper. So we have 12. And the superatom counting rules tell you that 8 is shell closing, so you have 4 too much, and they are kicked out of the sphere of the superatom to be exo. So this di-zinc unit does not contribute to the superatom closed shell situation of the octahedral packing. Now, why is our system integrating all metals in high symmetry? This is just because we reduce the total valence electron count by the number of 4, because the CP star ligand is very the electron affinity of the CP star is very high. So it takes away an electron from the metals to CP star minus. So we have not 12 electrons, we just have 8 electrons. And 8 electrons is 1s, 2, and 1p. 6 makes 8 from the superatom model. Now we have lots of different cases, and I skip that. I don't discuss that. You believe me that we can continue this forever. Now we go to the living library concept. If it's true that we can make many related intermetallic clusters being metastable and wrapped into hydrocarbon environments, some of them will fulfill the superatom concept. In that case, they might be rather stable. Some of them would not. They may be open shell, or they may be completely different in the terms of the electronic structure of the cluster. Then we would like to find a way to capitalize from this chemical complexity. So we intentionally drive our chemistry to provide a huge mixture of species. And the challenge will be to shine light into this mixture without isolating individual components, because if we go for isolation, we change the system and we may lose information. So we just then get access to those things we can isolate, and we throw away lots of things we don't know about it. So actually, we changed our strategy. Years, 10 years, 20 years, I'm honest to you, for the whole of my career, I have been hunting for the stable candidates by isolating single crystals from complex mixtures and wrote papers on that. Now we reverse the whole thing. We do no longer hunt for the most stable ones. We try to identify the labile ones. That is why we create this dispersion and mixtures. So we keep the chemistry of creating the mixture constant. Then we have to solve the identification problem of the mixture without separation and isolation. And we have to find a way to connect this to reactivity. And this is what I'm going to tell you now, how we do that. This is how such a mass spectrum looks like when we create a huge diversity of species. These are hundreds of peaks. Many are very low intensity. Many are fragment peaks, because a mass spectrum is, you put energy in your molecule and you destroy it. So you have molecular ions and you have fragments in parallel. Then the ionization efficiency of each of the clusters may be different. And it's very difficult to correlate the intensity, the ion current in the mass spectrometer, with the physical concentration in your sample. So the only thing what we have are these peaks. Now what we do? We do a double labeling strategy. That means, since we have to have a resolution of ±1 hydrogen atom, with high precision, we must rule out all coincidences of overlaying masses and so on. And we do that by a double labeling. We work with 68 labeled zinc. You can buy 68 labeled zinc metal. So I must make my students buying 68 labeled zinc foil, then doing all the chemistry to make the zinc chloride and then the zinc CP star. You can imagine this is work. And we label our hydrocarbons. Either we deuterate it or we put in an ethyl group. If we do that, the unlabeled and the labeled will be differentiated by the delta 14. And we have a differentiation here by delta 2. And with these two independent labelings, we can make 3 experiments. So the starting experiment without labeling, then the experiment with the 68 labeling, and then the experiment with the ethyl labeling. And with doing that, we can see these shifts of masses. And by analyzing that with a fitting program, we can precisely assign some formulas to each of the peaks in the mass spectrum plus minus 1 hydrogen atom with a very high resolution up to the limit of our spectrometer. Now we have to differentiate between the molecular ion and the fragments, because only then we can say how many species are we seeing. This is done in our mass spectrometer by the modulation of the so-called collision energy. People do this the same in protein chemistry and peptide chemistry. So if you have a protein and you would do sequential analysis, you modulate the collision energy in your mass spectrometer. What happens is the following. If we have a molecular ion and we vary the collision energy, CE is collision energy, and if the intensity of the peak goes down, more collision energy, intensity of the molecular ion goes down because more fragmentation. Other way around, if the collision energy is going up and our intensity of the fragment or of the peak we are testing is going up, it must be a fragment. Again, molecular ion, intensity of the peak goes down if we raise the collision energy. Fragment, intensity of the peak goes up if we raise the collision energy. So we can discriminate between molecular ion and fragment. And if we have a situation like this, then we have an intermediate fragment which is then fragmented again. By doing this, we can assign all peaks in the spectrum manually, of course. So I have to give credit, a lot of credits to my students, because it's brute force work. Every peak has to be assigned. And if we do that, we get this kind of list. And all these lists have been assigned. For example, I take out this one. This is the copper 7 zinc 3 CP star 3 times mesotyl 4. And this is a molecular ion because the fragment intensity goes down when we erase the collision energy. So now I skip 3 slides because this is your contribution. I will be very, very brief. If this needs to be discussed, and here are the experts. Now we give the sum formula, which is precise and no question about it. We give the sum formula to our theoretical partners, nothing else. And the only thing what they know is what is written in here. Now the question is, how does the thing look like? And they can solve this problem. This is not so different from what people do when they do cluster science in the gas phase. Imagine you have, let's say, a copper zinc aggregate of 20 atoms. You make it by evaporation of brass alloy, and you analyze what is flying around in your mass spectrometer as naked clusters. It's on the femtomole level, and they can do photoelectron spectroscopy with that or some other spectroscopies, and they get some spectroscopic traces. They do the same. They have the spectroscopic information, and then they model the spectroscopic information by guessing the structure. So this is kind of an iterative process. So what we do is very similar to what they do. The complexity is higher because we have the ligands. Okay, so this can be done in a 3-step process. So first, you generate kind of classes of aggregates where you do not take into account the difference of the different metals. And this can be grouped into classes by some some clever techniques. I'm not going into detail. Then once you have that level done, then you can put in the differentiation of the two different metals, and then you have lots of permutations of the positions. And then again, you have to be very efficient, and this is why the computer science comes into play. Once you have done this with a reduced configuration space, last step is putting on the ligands, again, randomly putting them in the system and minimizing it. And since we have a handful of isolated, structurally precisely defined clusters, we can calibrate the methodology against the experimental, in quotation mark, truth. I have been choosing a simple example, but we can do it for more sophisticated examples as well. So we give them the sum formula, they give back the structure with the metrics and everything, and we can compare it with our experimental structure, and in all cases, it fits within the error of acceptable level. So that means, even though we cannot isolate many of the interesting clusters and we are blind for their structures, admittedly, they will give us a good guess how the cluster structure might look like. And we are convinced that it's clever to believe that this structure is true, because we have a growing list of each of the ones we can isolate and calibrate against. The list of good fits is getting larger and larger and larger. So we are very convinced that the ones we cannot access experimentally, we have a good guess of the potential structure. Now, how does this come together in probing reactivity? Now again, imagine we have this solution. We have these 20, 30 species running around. We have a time evolution. So we initiate the cluster growth, 1 hour, 2 hours, 3 hours, some. If we want to probe reactivity, then we, for example, probe reactivity related to some interesting catalytic transformation. So for example, CO2 reduction. How would we do that? We have our cluster mixture, we have hydrogen gas, and we have CO2. Now we have a lot of opportunities. We can first make the cluster library, and then admit the hydrogen, and then the CO2. Or we can have the CO2 and the hydrogen there in the presence of creating the library. Or we can first create the library, wait, then add the hydrogen, wait, and then add the CO2. Imagine the parameter space of this kind of experiments. It's enormous. At the moment, we have no systematic logic to reduce the parameter space by a rational kind of thinking. So we did it by gut feeling. So the gut feeling was, let the library first grow a little bit. Then do a little bit hydrogen or do a little bit CO2 and look what happens. And then find out what would be the best sequence. So library generation creates us a starting point. Then we can put in CO2 without hydrogen. This is what is shown here, and we can see what happens. We see this kind of species, and we see this kind of species forming if we add CO2 to our primary library. And the calculation output from the partners tell us, in this case, when we have the CO2 around, the CO2 will insert into a carbon metal bond, which is not a very spectacular reaction, which is known from Grignard chemistry. This is not directly related to catalysis, but it makes sense. So this is for sure from the mass spec, and this is the calculated good guess of the structure. Now, it can be more complex. We can use first CO2 addition and then hydrogen addition. Now this one, this mass spec is the one we create when we have the library generated, wait a little bit, and then add the CO2, wait a little bit, and then add the hydrogen. Now look at this situation here. There is nothing. and there are two peaks after we add the hydrogen. This one is a molecular ion, this one is a fragment, and the difference is kicking away 1 Cp star. So this one is new, and this reads in that way. It is a copper 11 zinc 6. It has 2 CO2s attached, but also a formiate species. In this case, the CO2 is inserting into a metal hydride. And this is now going closer to the catalysis mechanism, because the CO2 reduction on copper zinc based catalysts is known to have a formate as an intermediate. So this experiment showed us, in principle, our cluster libraries simulate or mimic mechanistic intermediates which are known from the heterogeneous catalysis work on solid state materials. Now, last example. Again, we create the library, and then we put in simultaneously an alkyne with a triple bond. It's hexyne, where the triple bond is symmetrically in the middle. It's free hexyne. And we have hydrogen present. And what we see is that we have now a catalytic conversion of the hexyne to the hexene. It's a semi-hydrogenation. It will not hydrogenate to the hexane. It stops at the semi-hydrogenation, which is an important process also in the industrial purification of hydrocarbons. And if we analyze our abundance of species in the library, we find a new one. The new one has a copper 9, zinc 7, 6 Cp stars, 3 C6 units, so 3 hex units, and 3 hydrogen atoms. And the calculation framework reads out something like that, where we have a complex copper zinc cluster, and one phase, you will see in a minute more in a better image, and one phase is capped with various forms of hexyne molecules having 2 hydrogens, 1 hydrogen, or being a hexyne molecule just attached to the cluster surface. Now, what we could do, and this is why we are very proud of the result, and the referees have also been kind of puzzled. And this is sometimes when it's good that the referees kick you a little bit in your ass, as they did with the first manuscript. We got back some kind of first review reports which have been encouraging, but very critical. They're saying, there's potential and so on, but there is not a kind of a mind-blowing, really convincing result there. So once we saw this kind of catalysis going on with the whole library, and we found a new species formed, we were looking at those species in the library which disappear. So there are species which stay, for example, the triangle. The triangle is a dead thing. It just sits there and it's lazy. Others as well. And some disappear. I don't know what my student did to choose one of the disappearing to hunt for. So he was choosing this one, the copper 4 zinc 10 cluster, which we have not been paying attention before. It was around in the library all the time, but we never made an effort to enrich this one, to separate it out, and to crystallize it. My student did it in 7% preparative yield, 65 milligrams of this particular cluster he was able to accumulate after iterative, batch-wise work of, headaches of weeks. So he was able to get hands on this one. So this is a real experimental structure. And this is one of the clusters which disappears immediately when you add the hydrogen and the alkyne. So we were speculating, okay, this one is sensitive to these reactants. If this is sensitive to the reactants, there must be something. So we made it, we took it, we dissolved it, so we have now a single species. Now we take this single species in a solution, add the alkyne and the hydrogen, and the species, this one, is disappearing immediately. And this one is the only product of significance left over, I tell you. So this is the one which we made. We added the alkyne and the hydrogen. This is the spectrum of this experiment. This is the position where this one should be, it's gone. And we have this one appearing as a new species. This is the molecular ion. This is the isotope pattern of this particular thing. And these gray ones are all the fragments we can assign to the fragmentation of this peak here. And all these grays here are also fragments which come either of the fragmentation of this or a nasty impurity. This is an impurity, we cannot get rid of it, but this impurity is not sensitive to the alkyne and the hydrogen. It stays. So we have an almost pure situation. Message is, we could show that this cluster is a pre-catalyst in the chemistry of the alkyne semi-hydrogenation, and there is a huge reorganization of this cluster under the conditions of the ongoing catalysis. So this is how this cluster looks like as it comes out of the computer. And since I am trained as a skeptical chemist, as an inorganic synthetic chemist, I don't believe what the computer is telling us. I just hope it might be true. So the challenge, of course, when I talk this story to my community is, Professor Fischer, Roland, we only believe you if you put this as a single crystal structure on the table and show it to me in a vial in some yellow or brown or whatever Bordeaux crystals, then I believe what you have. If I then say, ha, this is an unstable species, too difficult to isolate, they would say that you don't believe because you have a mass spectrum, you have an ongoing catalysis, it lives under your conditions, you must be able to isolate it. We are working on it. So this is exactly what we wanted to have. We have the copper inside, we have the zinc outside. This emulates a brass phase, a copper-rich brass phase, where you have a copper phase and you have a bulk which is alloyed. And this is just the hydrocarbon protective group capping, and it's exposed here for doing some chemistry with our substrates. So that would be the coordination of the parent substrate, the hexine. That would be the coordination of the hydrated one, the hexene. And this one is difficult to see. This is a carbon atom which is bridging two coppers. This is the hub-to-1 mu2 hexenyl. There's just one hydrogen atom attached to the triple bond. It's just too beautiful to be true. Summary in perspectives. I think I could convince you that the combinatorial cooperative organometallic chemistry creates a platform where you can make a diversity of species, and you run into selectivity problem, but you have rich chemical complexity. So we can take advantage of fundamental organometallic reactions, and we can play with nucleation, growth, and cluster degradation, etc., etc. We have to look at the library generation. We use the mass spectrometer to shine light into that by monitoring this evolution. And the library is the library generation, and library evolution has two aspects. One is related to the generation and how the library, when we generate it, evolves over time. And when we add substrates like the alkyne, the hydrogen, or the CO2, we call it perturbation. This is basically we interfere with the intrinsic property of the cluster library if a chemistry is going on which is catalytic, and this may also interfere in a huge way in terms of reconstructing the more labile clusters which are pre-catalyst in this scenario. That is the goal, hunting for the labile ones which do the reconstruction connected to catalytic transformations. Thank you very much.
It's open for questions. Just raise your hand. I'll provide the microphone for you.